Okay, I'm going to start. This presentation I've done a few times, and it ranges in length from about an hour to about an hour and a half. And I've got 50 minutes, so I'll try and make sure that there's space for questions at the end. If not, please grab me around the conference, and I'm happy to talk about any of the things we're going to talk about today. So let's get going. My name's Dave Farley. I'm going to be talking about the process, technology and practice of continuous delivery. One of the things that I have in my relatively recent past was working at a startup company about the time where I was thinking about the ideas of continuous delivery and kind of writing a book about it. So that was a wonderful experience in being able to try and explore some of the ideas and approaches and techniques and apply those in a greenfield environment. And that's largely what I'm going to be talking about. I'm going to be using that experience somewhat as a model to explain some of the concepts and approaches that are common in applying continuous delivery projects. So I'm not trying to particularly sell you my project or anything. I'm just trying to use that as a model for how things worked. So I want to talk about what continuous delivery is, the real world of it. It's a big, complicated thing. It's a very holistic approach to software development, and there are lots of wrinkles and awkward bits to making it work effectively. So how do you apply that in the real world? And I'm going to use examples of some of the supporting tools that we built in this greenfield project to demonstrate some of the problems that you might run into and some of the techniques that you can use to evolve some of these. As I said, I'll try and make room for a Q&A at the end. So what is continuous delivery? For a start, it's a phrase that's used in the Agile Manifesto. In fact, it's the first thing in the Agile Manifesto, which says our highest priority is to satisfy the customer through early and continuous delivery of valuable software. It's kind of the logical extension of continuous integration. Can I have a show of hands? How many people use continuous integration in your daily practices? As a matter of interest, how many people use continuous delivery in your daily practice? Cool. So if you're familiar with continuous integration and the idea of trying to make sure that your software is working effectively almost all of the time, that's kind of part of the picture. But what you really want to see is it going to work all the way through to release into production? What you're trying to get to is we're trying to get an effective feedback loop. We want to have an idea, get to that idea into the hands of users that are going to make it valuable and so on. So we want to do this stuff early. So it's kind of the logic, taking the idea of continuous integration and extending it further across the software development process. As I said in my rambling start, it's kind of a holistic approach to software development. All of the bits in the process are important, and all of the pieces are kind of useful in terms of the way that they interact with one another. I'm not saying that this is a very prescriptive thing. That's not what I mean. The point that I'm trying to make here is that if you think about software development as a whole process and think about how are your requirements sourced and how do you prioritize those and how do they feed into the development, it has an impact on how you get the software ultimately into the hands of users. So all of these things can have an effect on what our ideal of trying to get valuable software into the hands of our users. Every commit creates a release candidate. This is one of those kind of thoughts that I found useful when I was kind of started exploring these ideas. If you think that every time you make a change to the software, it's giving birth to a potential release candidate, the rest of the process is about trying to prove that release candidate is not fit for purpose. You're trying to identify weaknesses and throw it out. Finished means released in the production. We've all been in the situation where our bosses come up to us and say, how far are you through with this vital task that you're working on? And say, I'm 80% done. And what that really means is that I've got 90% of the time left to finish off the 20% that I haven't finished yet. We're useless at estimating, so let's try and avoid that. Let's try and count what really matters. And what really matters is useful software in the hands of users. So it's not finished until it's released into production. I've talked a little bit about this already, but why continuous delivery? we want to have these ideas, we want to get them into the hands of our customers, and we want to evaluate the effect that has. We want to, as human beings, the excellent keynote that we've all just been watching, Kevlin's right, we're weak and fallible, and we make lots of common sorts of mistakes. And so the scientific method, one of the most effective approaches that things that mankind has ever created, is a way of avoiding that. And that's centered on the idea of establishing a feedback loop, making sure that we try an idea, we find out where it's strong and where it's weak, and we refine and we iterate, we keep changing things. So trying at the start of a project to design all of the features of a 3-year-long project is probably not going to be very effective, because we're probably going to get it wrong. So it's a good idea to get things out early, try them out, see if they work, and where they don't, refine them and correct, and so on. So in our idea, what we'd like to see is we'd like to minimize the time that it takes from having an idea that seems useful to our business, getting it into the hands of a customer, and seeing if that's effective. Sadly, most software life cycles are typically slow, inflexible, expose risk late, and are high cost. It does the opposite of what we would like to do. Lean thinking, coming from lean manufacturing, which kind of revolutionized the Japanese economy after the Second World War and lots of other things, starts with these tenets. It starts with the idea of delivering things quickly, build quality into the system, optimize the whole process, eliminate waste, amplify learning opportunities, make decisions late in the process, because then you'll have the most information to make the best decision, and empowering the team. Let the people that are actually doing the work decide how best to do their work. And these are good principles. The guy that came up with these based them again on kind of the scientific principle. He was looking at ways in which to use the scientific method in his case in manufacturing, but in general, applying that to processes of thinking, getting the benefits of the kind of skeptical mind approach of science, trying things out and experimentation, getting that into other fields, and that was a lot of where this came from. And I think that there are commonalities to that to most agile processes, and certainly the thinking behind the way that continuous delivery works. So I've talked already about feedback cycles, and what that really is about is if you think about the standard software development process, we start off with an idea, we look at getting that to the point of release. And during the course of that, if we're working effectively, what we want to do is that we want to set up a series of feedback cycles so that we can get early feedback of whether this, whatever step it is effective. At the smallest scale, there's kind of various layers of this. We've talked about one in the previous slide. There's the idea, getting some software into the hands of our users, and evaluating whether that's a good idea or not. That's kind of the outside loop here. But there are other loops in the process. If you're doing test-driven development, you've got the inner loop where you kind of write a test, see it fail, implement the code to make the test pass, see it pass, moving on. And this feedback loop is central to the idea of trying to build on solid foundations, proving that your work is good and effective, and that it's doing what you intend it to do, rather than making a guess, crossing your fingers and hoping that by the time you finish your bit of code 3 months down the road, it's going to integrate with the bit of code that another team is doing independently of you. By shortening the cycles in the feedback loops that are implicit in the approach to software development, we improve the quality of the throughput. We improve the quality of the process as a whole, and finding ways to implement and make those feedback loops short and effective is very important and very kind of fundamental to implementing a successful strategy. And that's kind of true at whatever level we're talking about it. It's true at the testing level, it's true at the testing out the requirements level, it's true in the way in which the teams interact to talk with quality assurance people or business people. All of the things that people in the audience might be familiar with from agile approaches to software development. Fundamentally, it's about trying to get these feedback cycles effective and as short as possible, so that we know where we're going wrong. Most of the rest of this conversation, I'm probably going to be talking about this end, because that's mostly, as developers, as I am, and most of you are, I guess, this is where we spend a lot of our time. But I just want to leave, I just wanted to make sure that we're kind of positioning this in the overall life cycle of the software. But most of the rest of it, I want to be talking about the mechanics of dealing with these problems in the actual production of the code and the release into production. This is a shameless plug of the book that I wrote with an ex-colleague of mine, Jez Humble, which has been gratifyingly successful from my point of view. But there's a lot more detail and depth of this kind of stuff that I'm talking about here in the book, and there's a good website that Jez Humble runs that has other thoughts and ideas that kind of come from this sort of thing. So the principles of continuous delivery. Fundamentally, what we want to do is that we want to build on known good work. So we want to create a repeatable, reliable process for delivering software. What that means is that we want to try and eliminate, as far as we can, the room for human error. I don't know how many of you have spent time in a data center or at a late night trying to hack the config to get software out into production because it didn't quite go as smoothly. I spent way too much of my career doing that at one point, and came to the conclusion that it was a very poor use of my time, a very poor use of my family's time, and I wasn't there at weekends because I was busy releasing software somewhere, and none of us were enjoying it very much. By looking at ways in which we can do this more effectively, I get the benefit of not spending my weekends in data centers, but the business gets the benefit of a system that's less likely to go wrong because it's going to be built on more solid foundations. If we want to do that, if we want to automate things, then we've got to make sure that we've got a fairly stable platform, which means that we've got to keep almost everything under version control. And by this, I don't just mean the code, the source code for our application, the configuration for our application, the configuration for the environments in which our application runs. Almost everything. There are many companies now that will release their software every time a change is made. It will go through a series of automated steps and end up in production without any human intervention. I'm not suggesting that's right for all organizations, but it's achievable. And many of these companies are building big, complex software. This is not just for very simple, trivial web applications kind of thing. And one of the counterintuitive things about software is that if something's hard and tricky and awkward and nearly always goes wrong, we should not do at least what I tend to do and try and avoid those sorts of things. We should do them more often so that we get good at them, we get effective at doing those. So if it hurts, do it more often and bring the pain forward and find ways to eliminate the pain in the process. I spent several years of my career as a consultant, and often I'd be involved in conversations in terms of the trade-off of spending time and somebody else's money on making sure that we were generating high-quality work versus the get it out and get it shipped kind of answer. I can't give you any metrics about this from a personal experience, but my belief is that time spent in quality always repays. If you're writing code and you're looking, that should be as good as you can make it and as reliable as you can make it, because what tends to happen is the thing that Kevlin was talking about in the keynote. We tend to defer the pain. We'll take the quick value of writing the code and not testing it sufficiently, and we'll forget about the subsequent months that we spend trying to discover awkward, difficult to identify bugs in production. Those costs are real, and they're costs that compromise us as a software development community, because we're not doing the things that are the fun, exciting, interesting bits of being creative and building new stuff. We're digging around the guts of log files from production and scratching our heads as to why this really weird, obscure thing is happening that we can't explain. Focusing on the quality of the software and asserting that quality is there is a way of paying for that time ahead, and it nearly always pays off. There's a great book that I'm in the middle of reading at the moment, excuse me, about HP. They've revamped their approach to firmware development for all of their printer ranges. They had horrible problems. They worked out that they were spending, of the total development effort, 5% of their effort previous to their changes was spent on actually developing new things. All of the rest was kind of maintaining the status quo, making sure things didn't break, porting stuff between the different individual branches of code that were maintained for their vast range of printer products. They've revamped the whole team, and they are now more than 10 times as productive as they were. They're now spending more than 40% of their effort on doing new things, productive things, because of applying ideas that are very similar to this. They came across it more from an independent route. It's a very interesting read. I recommend the book to you. Sadly, I haven't got a link to it in this presentation. But done means released. We've already talked about that. We can't, any time that we say that we're finished and it's not really released and in the hands of the users, we're fooling ourselves. We don't really know. Until it's actually being used, we don't know whether it actually works. Everybody's responsible for the release process. If you think about the typical release process in any organization, really, however big or small, the scope of the release process crosses boundaries. The business is interested in the release. The testing community are interested in release. The ops community are interested in the release. The developers are interested in the release, and the customers are interested in the release. Everybody has a stake in the release of new software, and so making sure that you get the responsibility right, making sure that the right bits of it, the responsibility for that process, are owned by the right people is important. I think it's very common and very easy and very human of us to say, that's not my problem. You know, I've finished the development. Testing's not my problem. Somebody else can write the test. They can look after that, make sure that everything works. Well, that doesn't really work. Everybody needs to work together to achieve this. And this is the system that I'm going to describe through the rest of this presentation in terms of how it works and the life cycle of releases. Looks very complicated, and it is. And the infrastructure to test and evaluate release candidates as they flow through this system is complex. But we didn't start there. We started simply and continuously improved how it's working. I've not worked for this company now for nearly a year, and I'm damn sure that it's continued improving, and if I were to go back and look at it now, the system would be different. It would have evolved. It moves on all of the time, because that was the nature of the team and the way in which we owned the system. So, practices of continuous delivery. Build binaries only once. One of the mistakes that I did early on was, when we were releasing software, we'd target a particular environment, and we'd build the software for that environment, and we'd build in configuration options and so on as part of the build process. What that means is that there's room for error, and I worked in one project where we had some software that worked fine in the test environment. We put it into one of the production environments, and it broke catastrophically. It was really bad. And it took us weeks to figure out what was going on. And what was going on was that there were a set of libraries and sort of environmental dependencies of the software that were different in this one environment to the test environment where we'd run. It was a compiler difference. There was a version we were using Java, and there was a difference in the version of the compiler that we were using, and so when we built it for that target, we got a different result. Use the same mechanism to deploy to every environment. This is part of the point that I made earlier of if something's painful, do it more often. If you rehearse the act of releasing software and practice it, that's a good thing. It means that at the point at which you're going to perform the release into production, you're pretty sure it will work. If you do that in a fake way and kind of you do all of the activities and you cycle around until you're about to release it to production, you're going to find out errors late. You're going to find out the errors soonest if you use the same mechanism. So for the release process that we built for our software in the projects that I'm going to describe, we built tools to help us to deploy the software. Those tools were what a developer would use to run the system locally on their machine. We could deploy the entire software stack for a multi-user, 100-node distributed enterprise system on a single laptop. It would groan a little bit under the load, but it would run, and it would run all of the tests. So we could do things. Because the environment was constrained, we could test it in different ways. We could fake failure cases, fake disconnections in the network, and all those sorts of things very easily. And the mechanism to deploy that software to my laptop to run those sorts of tests was identical. It was the same technique, the same code that was used to deploy the software ultimately into production, where we'd got a distributed node in multiple data centers of tens and hundreds of different servers. If anything fails, stop the line. Remember the idea of the release candidate. Every change to the system gives birth to a release candidate that may, if it's lucky, make it through to production. But all of the testing is going to try and prove that it's not fit and to throw it out. If any of those tests fail, you don't fix that release candidate and stop everything else. You throw that release candidate away. You go back to the head of the line and you make changes, and then you feed it all the way through again. You don't try and patch it up halfway through. The company that I've been talking about is a company called LMAX, and these are a company that do financial trading. You can go and sign up for an account and trade. It's mostly FX, foreign exchange, but other kinds of commodities too. You can trade on there, and it's a very high-performance system. The reason that I'm describing this is not because I'm trying to necessarily encourage you to go and trade on LMAX, but it's a big system. It's got all of the problems of a big system. It's got a matching engine. It's an exchange. Trades will come in and they'll be matched in the exchange. It's got different communications channels with the outside world, a variety of different protocols that will interact. There are web applications, there are custom protocols for exchanging data with market makers and high frequency traders. There are all sorts of things, clearing organizations where we need to provide information to report the trades that have been made. All sorts of different complicated environment. It holds assets worth millions and sometimes billions of pounds. So it's important. It's not a trivial system by any sense. As I said, at the time that I was there, it was deployed in a cluster of 100 or so server nodes. So it's a fairly complicated system. as I say, the reason that I'm trying to do that is just to position that idea. I'm not talking about some simple kind of mom and pop website here. It's not a trivial system. What I want to describe now is I want to describe the kind of continuous delivery process. So how this flows through. All of those of you that put your hand up when I asked if you were doing continuous integration, you'll recognize the first bit. So the typical development process in terms of implementing some change and getting it through and released into production starts with developers pairing. And we nearly always wrote our code in pairs. It wasn't mandated, but it was the common way of working. The pairs would work together, and when they were happy, when they'd run the tests locally and prove that they were passing with the latest version of the code, that it integrated well to everything, would commit their changes to the source code control repository. We call this the commit stage of the process. A source code, a build management system is monitoring the source code, the source repository, and when it sees a change, it's going to trigger a build. It's going to do some evaluations that will hope to catch the most common errors that we're likely to introduce at this stage. It's going to run all of the unit tests and a few other tests, which is why we don't call it the unit test stage. The goal of this stage is to try and prove that the commit that we're making is not going to destroy the world if it goes further down the line. If this is successful, the outcome of the commit is stored in the artifact repository. Remember what I said about building the binaries once. We're going to store the outcome of this build, the jars that we're going to ultimately deploy into production, in the artifact repository. And if this release candidate makes it all through the system, these are the jars that will get deployed into production. We're not going to build them again. So we've automated the process. We're absolutely certain that every bit and byte of those jars is the one that we intend. If this fails, we don't commit to the artifact repository, which means that we don't expend the resources further down the pipeline that I'm going to describe in a minute. And the developer's job then is to fix things as quickly as possible. This is, as I say, this is normal continuous integration. We aim for this process to be fast. We want this to get, this is a tight feedback loop. We want the developers to have a response to their commit in under 5 minutes. Ideally less than that, but 5 minutes is a good benchmark. If you're getting to 10 minutes, start looking at ways of making things go faster. Optimizing the commit stage is important because it kind of oils the wheels. One of the principles kind of underneath the way that continuous delivery works is small batch sizes, making sure that each change that flows through the system into release is small. That means that any change has a limited impact on screwing things up. It's easy to recover from. It's quick to identify what's gone wrong if things don't work out, because the change is small. If that's successful and the commit build has said everything's okay, the developers are happy. They can move on and they can start working on something else. The normal kind of continuous integration mantra, they're kind of waiting for that result. They're not doing anything else because maybe things might go wrong, and they want to be in the place to fix things as quickly as possible. We had a team rule that if you broke the commit build and you couldn't fix it within 10 minutes, you'd revert your changes. Other people are more serious than that. The HP guys that I was just referring to earlier, if you broke their early stage build, they'd revert your changes automatically. And you'd have to then kind of figure out how to fix things elsewhere. It's not a bad strategy. The next stage is acceptance testing, and these are really functional tests. What we're trying to do here, unit tests are wonderful things. They assert that the code is doing what the programmer thinks it should do. But by definition, they tend to be close to the design of the system. This in some ways is a good thing. It means you can get close, you can abstract the unit tests away to focus them very, very closely on the code that you're writing. And if you're doing sensible things like kind of business-driven design, so you're designing your unit tests in a way that kind of assert the business ideas, not just the technical tinkering with the class, that's all good stuff. But even so, they tend to be close to the code that you're writing. What they tend not to do so well is assert that the code is doing what the business intended to do, or even more importantly, what the users intended to do. So acceptance testing is really about that. It's really about ensuring that the code is going to be exercised in a way that's more lifelike, that it's going to be tested in a way that evaluates whether the business goals of the story that you're implementing are fulfilled. This is not watching the source repository. This is watching the artifact repository. This is important. Remember what I said before about the commit code. If it failed, it wouldn't commit the artifact repository. This is a gate. This means that the acceptance test build only gets to look at code that the commit stage thinks is good. The acceptance test build is going to go and run the swathe of these more realistic tests. And for most environments, what makes sense here is to bring the application up, run it in a realistic context, run it in a lifelike, production-like environment, and evaluate it there. The closer to production that environment is, the more valuable the feedback that you're going to get from that acceptance test state. If that all works okay, the release candidate in the artifact repository is tagged with a status saying that it's passed the acceptance test. For us at LMAX, sorry, I'm going ahead. Manual testing. I'm going to talk an awful lot about acceptance testing, and I think that anybody that does regression testing with people is doing it wrong and missing the point. People are useless at regression testing. People are not good at complex, repeated tasks. We shortcut things, we skip things, we forget things, and that's not our strength. What people are wonderful at is being creative. So they bring a different approach to testing. And what's much more effective for people to do is kind of exploratory testing, investigative testing. Does this application kind of feel right? Does it hang together? Does it make a sensible, coherent user experience when you bring all of the features together? If I do this stupid thing, press these 5 buttons and sit on the keyboard, does it explode? If I upload a massive file through the file upload system, does it fall over in a big heap or break the security? It's those sorts of exploratory testing things, the creative side of testing that people are excellent at. So you don't want to rule, or at least we didn't want to rule people out of the testing process. There are something, writing an acceptance test, an automated test to assert that the color of a button is correct is probably not really worth the time. But writing an automated test to assert that the button is there and that you can push it and that when you do something happens probably is a good use of time. So we built manual testing as a stage in our process. If the acceptance test had passed, we would use the same deployment tools that the developers had used when they were building the tests in the first place, the acceptance test environment used to deploy the system into there to evaluate it. We use the same tools with kind of just a simple web application on the front of it to deploy it to a test environment. This is kind of an interesting. What we observed was that it kind of changed the behavior, it changed the relationship of the testers. Instead of them waiting for somebody to commission an environment for them to deploy some software for them to test, they would work more closely with the developers. They'd say they'd be working on a feature and say, How far have you got? Which bits are done so far? Okay, well, which release is that in? I'll pull that release candidate down and test it, and I'll test that far through. Which means that it was easier for us to kind of finish an iteration altogether rather than have an overhang of testing after the developers had finished. There wasn't a delay because people would work very closely. They'd be interleaving the work of manually testing features with developing features. It also means that you do stupid things. If you got some horrible blow-up in production that you couldn't figure out where it had come from, you could, once you'd identified that there was a problem, you could write a test for this, and then you could kind of binary chop the versions to see which version of the code the thing was introduced into to narrow down the scope of what could have caused this problem in the first place, and to better help you diagnose what was going wrong and how to fix it. Again, if the testers are happy with the software, that it fulfills their criteria, whatever those criteria might be, they can kind of tag the software, the release candidate, with a tag saying that it's passed manual testing. For us at LMAX, performance was a business differentiator. We were trying to build one of the highest performance trading platforms around, and we wanted to know the performance characteristics of our system lots of different ways. If any of you have worked in high-performance computing environments, you'll know that testing and evaluation are a crucial aspect of delivering high performance. Nearly all projects talk about performance being important. Sometimes it is, sometimes it isn't. Mostly some kind of stage to make sure that you're not doing incredibly stupid things is useful to evaluate these performance and other non-functional requirements. To use a horrible phrase, it's not non-functional, why do we care? But so performance we took quite seriously, and we kind of split it into two stages similar to the commit and the acceptance test stage. First, we would do component-level performance testing. For a component of our system, maybe the messaging system or the journaling system or the matching engine, something like that, we'd write a focused, almost unit-like performance test, which would assert that the code ran at a certain rate. If, for any reason, we did a check-in and compromise that performance, then we get a big red flag in our build monitoring system that would tell us that something had gone wrong, and we could then go and diagnose what we'd done wrong to slow things down. Again, this was an automated stage. It would pull a release candidate from the artifact repository, run the performance tests. If they were all passed, it would update the status of the release candidate. That's great. One of the distinctions that I kind of didn't mention between the unit testing and the commit stage and the acceptance test stage is that the acceptance test stage is kind of really good at finding out the things that you didn't expect. The nature of the failures that it finds are kind of different to the sorts of failures that unit tests find. This is not quite perfect, it's kind of a half-formed thought, but it does tend to discover the things that you didn't expect, whereas unit tests tend to just assert that you're not doing something incredibly dumb. I know that's not wholly true. That's not wholly true about unit testing, but the acceptance testing discovered more things. For example, ours was a big, complex, asynchronous system, and we would periodically have stages in the life of the application where we would get a lot of intermittent test failures. Nearly every one of those that we dug into, the intermittency in the acceptance test environment, was a real underlying cause. There was a real problem, some race condition between the asynchronous components of the system or something like that, that when we dug into, we found a real problem, which would have been hard to figure out how you would find any other way other than some very esoteric, weird bug in production that you couldn't tie down. Going on the performance testing thread a bit further, system performance would do the same kind of thing. It would run the whole system, so the component level performance testing was great at targeting those components that we knew were likely to be bottlenecks in our application. The system test performance would flush out any things that we hadn't thought about, that we hadn't identified as potential problems. So there we'd kind of bring up the whole system in a lifelike section of the production environment. The performance critical pieces were identical hardware, for example, to the production equivalent servers. Other bits that we knew weren't in the main flow, we didn't bother with so much. But that too would start the whole system up, run a battery of kind of load and performance tests. One of the things that we did is that we recorded the day of heaviest load that we'd had, where we had some problems in our application. We recorded that and then kind of scaled it up in the production environment so we could replay the scenarios, the mix of scenarios that interacted with the system, and check those any changes against those trying scenarios. If any of you are there doesn't look anybody in the room as quite as old as me, but if any of you did any Windows programming, there used to be a thing called a heap shaker that would move stuff around randomly. It was a bit like that, and figure out where you hadn't got your memory allocations right. Again, you're detecting a pattern here. If it's all good, it will update the status in the artifact repository. Ours was a very stateful application. We had, it was an exchange. We'd have large numbers of financial instruments that were being traded, large numbers of trades. We were holding positions for people, so we had money and financial assets that were being held, as long as lots and lots of other stuff. And so we needed to, that state was, because of the high performance nature of this system, was largely held in memory. There were some databases around for various things, but most of the stuff was live in memory, which meant that we had to migrate all of that state in the database and in memory every time we released the software. Which meant that we wanted to be able to rehearse that migration with lifelike data. So the staging environment was used to kind of take an anonymized cut of the current state of production data, move that into the staging environment, do a trial release of the software, and just evaluate that it just looks like everything's standing up, a few smoke tests to make sure that the software is working effectively, and so that we have a reasonable confidence that our migration of the data was effective before we actually release it into production. Again, this was kind of manually managed. We didn't wholly automate this, although at the time when I left, we were going further and further down the track of making that a fully automatic stage as well. I'm not quite sure where that ended up. Finally, if all of this is good, if a release candidate has passed all of these tests, then we have a fairly high confidence that it does what the developers think it's going to do. It does what the business wanted it to do because it passed the acceptance tests. It doesn't do any really quirky things because it passed the manual tests. It performs at the levels at which we intended. And it's going to work with the data that's in production now, before we released it into production. So we had a high confidence that at the point that we got to production, we'd push a button, it would deploy it to production, and it would work. Largely that happened. We had the odd difficult day. It wasn't perfect by any stretch of the imagination, but largely the vast majority of releases were simple, relatively calm efforts to take this complicated stack of software, configuration information, and data, and move it into production. When we got, just one more step. This whole thing, this automation of the software release cycle, is what's referred to in mine and Jez's book as a deployment pipeline. And the idea is that I came up with the term deployment pipeline. And the reason that I did it wasn't because I was thinking of kind of an oil pipeline that's kind of one long line through from check-in to production. More that it reminded me of processor pipelining. When a processor works on instructions, it will do branch prediction. It will figure out that the next few instructions depend on the equivalent of a branch, and it will kind of line up behind. So effectively what you're doing is you're doing a gamble. What the developers are doing when they do a successful commit in the commit stage is that they're taking a gamble that all the rest is going to be okay. They're going to then switch context, move on to the next thing that they're going to do, the new story or whatever else it is that they have to do, and they're going to assume that the rest is going to work okay. That's the gamble that they're taking. If they're right, then they're going to get all of this testing for free and all of this assertion of the quality of their commit for free, and being able to do other things in parallel. If they're wrong, something's going to fail down here. Their job at that point is to drop whatever they were doing and go and look into the problem. So they're kind of moved on to a new thing. They're kind of keeping half eye just to check that everything goes green as it should through the life of the deployment pipeline. But they're taking the gamble. They're doing the branch prediction of assuming that things are going to go well. Which goes back to the thing that I said at the start. The commit stage is intended to be a high-performance assertion of the most common, that you don't have any of the most common sorts of failure cases in your code. Mostly that's going to be unit tests, but there are other sorts of things. One of the things that we did to, not my choice, not my favourite thing, but we use Spring to do the wiring of our system together. And one of the things that I don't like very much about Spring is that you don't actually know that you've got the configuration wrong until runtime. It's not a compile time checked thing. So we built a bunch of tests that would kind of run up our Spring configuration and just assert, as part of the commit stage, that it was coherent, that it made sense, that it worked, that it built the application we wanted it to. So that we didn't find out later when we got to the acceptance test stage and it's too late to fix those kind of short cycle things. Okay, so that kind of describes the principal mechanism of how this works. I want to go into a little bit more detail of the acceptance tests because they're complicated things. And of course, there's a bit more to it to what I described. At the time when I left LMAX, we had something in the order of, I think it was about 20,000 unit test cases, something like that. And we had about 12,000 acceptance test cases. As part of our development, remember what I said at the beginning about this kind of being a holistic thing? This was kind of the acceptance testing in particular was kind of glued into our development process. So when somebody came with a new requirement, a story that said, we want this feature, when it's ready for development, the final stages of detailing that story is to say, okay, this is the feature that I want. This is the requirement that I want fulfilled. And here are a few acceptance criteria that say, when I know that I've got that feature, as a trader, I want to be able to register my credit card so that I can trade online. I will know that I've got that when I can register a credit card and trade. So those are acceptance criteria, following that requirement. And so it was a requirement on the developers to build acceptance tests, high-level, whole system tests that asserted those behaviors of the system. And the acceptance test environment is where they'd be run. As I said, so it would start with the artifact repository. So let's imagine a release candidate in the artifact repository. And the acceptance test environment has just completed a run. It goes and looks for the most recent release candidate in the artifact repository. The implication of that is it's skipping over release candidates that may have trickled in earlier, so you're not getting an ever-increasing tail backlog of work to accomplish. You're going to jump over, which means that there may have been multiple commits that might be feeding this acceptance test run. The acceptance test environment is going to pull down that release candidate, and it's going to, using the automated deployment tools that I talked about, it's going to deploy that to the acceptance test environment. We're then going to run a grid of test hosts that are going to fire a whole bunch of tests at this release candidate in the lifelike test environment for our acceptance tests. We had some tests that would run in other environments. If we were testing failure conditions where we were shutting down different services. You can't do that while you're sharing the environment with a bunch of general purpose tests. But mostly they would all run in a shared environment. And if it all worked, at the conclusion of the tests, the acceptance test hope would gather up the data and tag the candidates in the artifact repository. This is a graphic that one of my colleagues who is at this conference wrote to just visualize some of the allocation of tests running in the acceptance test environment. These are some of the different codes. So these are some of the tests that could run in parallel. These are time travel tests where we would artificially manipulate time so that we could do long running scenarios. And I can't see what the last one is. The next stage is if you've got multiple release candidates that are feeding into the process, then there's multiple sources of responsibility for test failures. So you need something that's going to flag what's going on. This is another kind of custom-built tool that we built for this project, and this is kind of what we call big feedback. The top level tells us what iteration we were on for those of us that were forgetful. The next level down is kind of the commits test stage, and this is saying the last 3 commits were good, and it says what versions they were and so on. The rest of it is kind of the rest of the deployment pipeline. And there are bits that would run static analysis of the code, the acceptance test summary, and some of the performance test stuff is further down here. This is what it looked like when things weren't quite so good. When we got a test failure, we kind of have a breakdown of the test that failed. And there's something weird going on here. We've got an analysis failure here. So there's a static analysis of the code is telling us something's wrong before it's even got here, and then we've got this failure. So it's not in a good situation. This is another tool that we built. There was a woman on the team, also a member of the LJC and here at the conference, Trish, who for a while kind of was the team conscious. She would stay on top of doing analysis of test failures and kind of point the finger and give chocolate bars if you were a good citizen, and stayed on top of fixing your test quickly and come and tell you off if you didn't. And one weekend, one of the guys knocked up Auto Trish, which was kind of doing the similar kind of analysis but automatically, and would report, and each test run got a Trish rank. You can see something bad happened here, and we kind of broke a series of tests after that test run. Maybe there's an intermittent thing going on here. Maybe there's something we ought to investigate because we've got a failure, some passes and some more failures. Maybe there's something more subtle going on here. It's quite of a nice tool. Several people have asked whether we were going to open source this. I'm not quite sure it's the sort of thing that you could easily open source because it was very tailored to our team, but it helped a lot. I'm out of time already. Can I have a show of hands? I've got 2 things that I'd like to kind of rush through and get in. Would you like to hear about strategies for acceptance testing or strategies for deployment? Deployment. Okay, so I'm going to skip over this. It was a good slide. I went a bit animation happy on this, but it's about raising the level of abstraction for testing and the importance of making sure that a break in your application doesn't break swathes of tests that aren't easily fixable. Come on. This is the domain-specific language that we wrote for testing. Again, some interesting stuff. Okay, so our deployment system was called Scotty, as in beam me up, Scotty. It was very simple. So centrally, kind of logically sitting on top of the artifact repository was a Scotty server. And then each node where the application could be deployed, whether it was a manual test environment, a performance test environment, acceptance test, or production, would run an agent, which would periodically ping back to the Scotty server and say, "Do you have any work for me?" And Scotty would reply with simple instructions like start, stop, nothing to do now, or deploy. Of course, it was a bit more complicated than that. Some of these environments were single machines, like the QA environments. Some of these environments were very production, were production, or production-like, a kind of vertical slice through the production hardware architecture of the system. And so how do you use the same tools to deploy to all those different environments? So the Scotty agents that ran at each of the nodes kind of had a series of definitions of what role they were playing. So one might be the matching engine, one might be the order management system, one might be a web server, and so on. So those kinds of roles, so on a high level. So that each agent knew two facts. One fact was, where's the Scotty server? And the other fact is, what roles am I playing? And that was it. So in the example of a single box system, a QA environment might be playing all of the roles because it's going to deploy all of the bits of software that make up that system. In production, each node is probably playing a specific role. It's targeted because that makes the operations team like that. It was a simpler model to manage those environments. For performance testing, some environments would be using a specific role, the matching engine, for example. Another one where we were doing something that wasn't critical to performance, some offline thing, we could double up and we wanted it to be there, but we didn't care whether it was fast or dedicated. Production, of course, was more complicated than that because, as well as the production site, we had a disaster recovery site in another data center, and that worked the same kind of way. So what was going to happen is when it saw a deployment instruction, it was going to pull down the artifact from the artifact repository. It was going to run the scripts that were the deployment scripts, which would read the role definitions for that server and deploy the right bits of software and start them up. It would stop the versions that were running. There was kind of a state machine that would run through. It would stop the versions that were running, pull down the changes, deploy the stuff, migrate the stuff, start it up, and assert that everything was looking okay before giving you a healthy status. This is a picture of the Scotty. It's not pretty, but it's got the kind of principal things that you care about. On the far left-hand side, it's the deployment revision. That was the build tag that kind of came from the version control system during the commit build, which lives with the release candidate through its life cycle. That's its unique ID. And it's got a do it button. So if you want to press the upgrade, you say, I want the third one down from the top. Do it, and Scotty would do everything else. It would issue the instructions, the agents would pick up the instructions and execute them. This is the panel, this is an example environment. I think this is the performance test environment, and you probably can't read the details, but there's some green stuff here. Basically, that's saying everything's running as it should, following a deployment. Each of the nodes is saying the role that it's playing. So this one's a payment gateway. This one's a database server, and so on. Here's a single box environment, kind of the same information, but just running on one machine. So you've got the same reports here. That's it. I'm afraid I am overrun by about 5 minutes. I'm very happy to take questions, but I guess I should let you go for coffee, and I will be outside. Please come and grab me and if you have any questions. Sorry it was a bit rushed.